Hello, this is Dr. Viv. I'm going to talk in this video about a very important principle known as the conservation of mechanical energy. Actually, I would like to start with something very simple, something that you've learned in calculus. So if you have, let's take F equals ma, Newton's second law, and for simplicity of discussion, forget about vectors and look at everything in one dimension. Well, this is m dv by dt, because acceleration is the rate of change of velocity. I can write this using the chain rule as m dv by dx times dx by dt. However, dx by dt is just the velocity again, so I'm going to get mv dv by dx. So multiplying both sides by dx, a process known as taking the differentials, I get f dx equals mv dv. So rather than say multiply both sides by dx, you would say taking the differentials. That's a fancier way of doing this. Recognize though that f dx, when integrated, is just the work done by the force. So I'm going to end up getting work done by the force, Wf, is equal to, well, the integral of v dv is half v squared. So it's going to be the change in 1/2 mv squared. Because when you take the integral, you go from initial to final. So the work done by the force, which is given as the integral from initial to final f dx, is equal to the change in the kinetic energy. This is sometimes called the work kinetic energy theorem. And it's a very important fact. In general, it can be generalized by summing over all the possible forces acting on a particle of mass m. Now, that is one viewpoint, and that's a new viewpoint that Newton completely missed. He didn't bother doing it, partly because he was so good at calculating that he didn't need the concept of energy. But later it was found that the concept of energy, aside from being useful in calculations, was a very useful conceptual tool to understand nature. What we're going to do is further refine this process. We're going to think of the universe as being made up of two kinds of forces acting on the object m. The conservative forces, which I'll call Wc, and the non-conservative forces. The work done by the conservative forces will be called Wc, and the work done by the non-conservative forces will be called Wnc. So what are conservative and non-conservative forces? Good things like gravity and springs are examples of conservative forces. It just means that the work done by the force does not depend on the path you take to get from I to F. Non-conservative forces are very sensitive to the path taken. So things like air drag, friction are good examples. Basically, the longer the path you take, the more friction will act against you. So these are highly path dependent. So you can break up the world into two parts. The advantage with doing this is that the left-hand side of the work energy theorem, which is sum of all the work done by all the forces, can be broken up further into two parts. Therefore, the left-hand side of the work energy theorem is the sum over all the works done by all the non-conservative forces, which I'll call Wnc, plus the sum of all the works done by the conservative forces, and that is equal to the change in the kinetic energy. Now, what is the big deal about doing that? It seems like I've just made my left-hand side more elaborate. The beauty is, for every conservative force, you can express the work done by a conservative force as a change in potential energy. So for any conservative force, let's call it that conservative force Fci, the work done by the conservative force Fci is given as negative the change in the potential energy U corresponding to the force Fi, F sub I. I'll call that Ui. This Ui is called a potential energy. So famous examples of potential energy include the gravitational potential energy, for example, UG. The gravitational potential energy as a function of y is mgy. It depends only on the height. And the potential energy of the spring, us, is a function of x, and that's 1/2 kx squared. One of the properties of the potential energy is that the negative derivative gives you the force. So if I take the negative derivative of the negative dug by dy is simply going to be the force of gravity, which is equal to negative mg. And that makes sense because the force of gravity is indeed negative mg. Let's try the same thing with the spring potential energy. Negative du by dx is just negative kx. And that's the force according to Hooke's law. So that also makes sense. So if you write it in terms of non-conservative forces plus conservative forces, then what we can do is we can take all the potential energy contributions to the right hand side. Since this is equal to negative delta ui summed over all I can take all those things to the right hand side. So I'm going to end up getting sum of all the non-conservative works is equal to the change in the kinetic energy plus the sum of the changes in the various potential energy ui summed over all I. So this is a fancier way of writing the work energy theorem. So I'll again continue to call this the work energy theorem. For non-conservative forces, because it puts non-conservative forces in the spotlight. Okay, what if the non-conservative forces are completely zero? Then we have a second statement. If WNC is completely zero, which means there's no friction, none of the bad guys exist, then we're going to have 0 equals the sum of kinetic plus the sum over all I of the potential energies. This is an important statement known as mechanical energy conservation. And this is the statement, this statement and the other one above are the things we'll focus on mechanical energy conservation in this video. Now, by the way, since change is final minus initial, I can write this as also K initial plus the sum of all these things. Usually in our problems, we have just spring and gravity, so I might as well just break it down for two things. UG initial plus U spring initial is equal to K final plus UG final plus U spring final. So that's an easy way to remember and write. And your formula sheet has got all these things. Let's apply it to these two examples here. I just made up two random examples to show you how easy it is to work out problems. Now, if you tried doing these problems using Newton's laws, you'd be completely powerless. You'd be paralyzed in the very first second. Because look at the shape of the hills. They're not smooth, they're not nice inclines or anything. So you can't do trigonometry. None of that stuff is applicable. The first example that we'll be looking at has got a hill which is completely smooth, no friction. A particle starts out with some particle of mass m, or block of mass m starts off with some initial speed at a height h above the ground, and this thing does some weird roller coaster like motions and ends up compressing the spring. Now there's some interesting stuff that's going to happen here. In the next video we'll explore possibilities of the block losing contact because of the curvature here. We won't complicate that in this video, so we'll keep things basic here since it's our first exploration with energy conservation. So our purpose is to find the spring compression. Now, how do you do something like this? You may think that this is a complicated problem. You may have to find out the speed here and then the speed there, but no. We only have to worry about the initial and the final. So let's just consider that to be our initial state and that to be our final state. Clever use of initial and final is very important in energy conservation. Now in this problem, there is complete smoothness, no air resistance, no friction, so I'll be using formulation 2. So I have the initial kinetic energy. Because WNC is 0, I can use mechanical energy conservation in that form. The initial kinetic energy is 1/2 mv squared, or mv naught squared rather. The initial potential energy, because I'm going to take the potential energy over here as 0. This is very important. You always have to take a reference potential energy. So with respect to that, the potential energy of the top of the hill is going to be mgh. Well, the initial spring compression is 0, so there's no spring compression energy, is equal to the final kinetic energy. Well, the spring is completely compressed. That means the block doesn't move. Gravitational potential energy, we have taken it to be 0 at the bottom, plus the final spring potential energy is 1/2 kx squared. That's it. That one-line equation is our answer. Solving for x, multiplying both sides by 2, I get rid of the half, and then I divide both sides by k and then take the square root. That's brilliant. In one line, we have been able to solve a physics problem. This is only possible with energy methods. Newton could have got this with some struggles. He'd probably ask you for the shape of the hill and everything, and you gave him the shape of the hill. He'll probably spend a couple of days doing it, and he'll end up with the same answer, not knowing why. I guess I'm just making it up. Newton was a very smart cookie. He would definitely know why. Let's do the second problem. In the second problem, there is friction. So we have to use the first formulation of the energy principle. In other words, the work kinetic energy theorem for non-conservative forces that I've written here. What we are trying to do is this. There is a spring of spring constant k. Initially it's compressed by some x, and then it goes forth like this, and then eventually it runs into this friction patch of mu k of length L, and it stops at P. The question is, what is the coefficient of friction? Now, once again, you might think this is a complicated problem because the spring is going to stretch out, give it some velocity, and then, but again, it all depends on what you call initial and final. I'm going to take the initial to be the spring in the compressed state itself, and the final to be over here. Then we don't have to worry about all the drama in between. So let us use the second formulation of the principle. The work done, non-conservative work, is simply going to be the work done by friction, kinetic friction rather. Now the work done by kinetic friction is given by the force of kinetic friction dotted with displacement. The kinetic friction always acts in the opposite direction as the particle's displacement, which is in this direction. So the displacement vector, which I usually write with this special dotted line, but I won't bother this time. So F dot D is going to be with a cosine of 180 degrees. So I'll get cosine 180 gives me -1. So that I'll get negative mu k mg, because that's the normal force, times L. So that's the work done by friction. All that's going to equal the change in kinetic energy, because this is what we're looking at. The change in kinetic energy. It's not moving initially, it's not moving at the end. So the change in kinetic energy is 0 minus 0, plus the change in gravitational potential energy. The final gravitational potential energy, once again, we'll take this to be 0. So it's 0 minus mgh. And then the change in the spring potential energy. The spring is completely compressed at the end, completely relaxed at the end. Initially it was completely compressed, so the spring at the end will have no energy, and initially it's got energy 1/2 kx squared. Once again, believe it or not, we're done. We'll just solve for mu k by multiplying the whole thing with a negative sign and dividing it by mgl. So that's mgh plus 1/2 kx squared divided by mgl. We have solved for the coefficient of friction of the friction patch.